Hey guys, Pankaj here. Welcome back. So in today's video, I'm going to talk about ridge and lasso regression. So we'll see what it is and where to use and what is the mathematical intuition behind it. Okay, so let me share my desktop. Okay, so here is the topic which I'm going to cover. What is lasso regression? What is ridge regression? Differentiation between lasso and ridge regression, and what is the mathematical formula for both lasso and ridge. Okay, and we'll take one famous data set called Boston house price prediction. Okay, in that I'm going to run both lasso as well as ridge regression and see how what kind of difference it can make and how you can do the feature selection using the lasso regression and a couple of plots so that you can get clear representation of the data, how exactly it is getting differentiated between lasso and ridge regression. Okay, so before that, I'm going to explain what is the mathematical intuition behind it and how it basically works. Okay, so first let's see one formula here. So the formula which we had seen for normal linear regression, right? So let me just type linear regression. This is also known as ordinary least square. Okay, so what is the formula? We have seen n, then I equal to 1 to n, y minus y hat. The one is the actual value and this is the predicted value. Okay, and the square. That's why it is known as ordinary least square. Now for the lasso, what same formula we'll be using, but there is one penalty added. So I'll tell you what is penalty and why it is added. Okay, so we are going to have 2n and I equal to 1 to n y minus y hat square plus there is one term called lambda, and here we will have j equal to 1 to, let's say, d or n, whatever, based on the number of feature it is selected. Okay, so j equal to 1 to d, and here we have slope. Okay, so you can directly write slope, or if it is presented by theta or omega, whatever you can write, you can just write. So this will be basically exactly absolute value of slope. There is no square. Okay, so I'll just mention absolute value of slope. Okay, and there will be very much similar equation for ridge also. Exactly 1 upon 2n I equal to 1 to n y minus y hat square plus this small difference. Okay, so j equal to 1 to n, and here we will have exactly square of the slope. This is the difference. Okay, so because of square, this is also known as L2 term or square penalty. Various names are there. Okay, and ridge is another name. Okay, and this is the absolute slope penalty I can mention. Okay, or absolute penalty, and this is also known as L1 term. So we have different name for lasso, L1 term or absolute penalty, and the for is we have L2 term. You can remember like this because we are taking the square of the slope. Okay, so that's why it is called L2 term or square penalty. Okay, so this is the mathematical formula behind it, and now let's see how it works basically. So I'm going to take another whiteboard here, and let's say you have data something like this. There's one data here, one data here, one data here, something like this. Okay, and assume that you have the best fit line like this. This is another data, and you got the best fit like this. Let me write best fit line. Okay, this best fit line you can think in this way. So let's say either you are running lasso or ridge. Let's say this lambda, basically this can be any float value. Okay, any float value. Similarly for this also. So if lambda equal to 0, what will happen? The whole term will become 0. Correct? If whole term becomes 0, means lasso or ridge both can become as a ordinary least square. Ordinary least square. It is as good as you are running simple linear regression. There is a formula. Okay. If you are getting lambda equal to 0 or setting lambda equal to 0, your best fit line will be like this, and this is where you can write lambda equal to 0. Okay, so this is your best fit. Now let's increase the lambda value. See what will happen. So before increasing the lambda, let's say you have another data set very similar to this. Okay, and here assume that I got the best fit like this. Okay, and let's say we have lambda equal to some value 10. Okay, so in case you got the best fit line this, and if you're going to calculate the sum of a squared error, right? So what will happen? Let's say this is the best fit line. From there, you calculate this value, you calculate this value, this value, this value. So your sum of squared will be very high. Why it will be high? Because your slope is exactly zero, correct? And because it is zero, you see the difference, error difference between the predicted. This is nothing but your best fit line, right? And this is also known as a predicted value. Predicted value. Okay, if you are going to calculate the square or difference between predicted as well as the actual value, it is going to be very high. That's why uh, the sum of square feature will be sum of squared value will be very high. So in case you are going to plot them, let's say this line represents your slope and the y-axis is representing sum of squared error. That is nothing but your ordinary least square, right? Square error. Okay. Plus, I'll talk about this term later from the last word regression. Okay. So let's say you calculated the slope and your slope was, let's say, we have 0, right? So assume that this was 0. Okay. So sum of square error when slope is 0, it is going to be very high. Somewhere here. This is your data point. Okay. Or the value of sum of squared error. Correct. Now let's say you are increasing the slope. Let's say I made the slope like this. Another best fit line. Okay. And this will be, let's say, lambda equal to maybe some value, let's say 20. Okay. In this case, what will happen? If you are going to calculate the squared error, this is definitely going to be lesser than this. If you calculate the sum of a squared error from this best fit line, you are going to have very less value. So maybe let's say somewhere here. Okay. This was, let's say you had slope was maybe 0.4 or 0.2. Okay. Now assume that again you took another best fit line. Okay. So from this also you will have some squared error which will be lesser than this. So let's say you got this. Similarly, you go like this, keep doing like this, and the moment you cross this line, again your sum of squared error will be increasing, right? Because let's say this is another best fit line because lambda equal to maybe some value, let's say 50 or some value you have taken, right? Other than 0, because 0 is your best fit line. So if you take another value, again your sum of squared error will be increasing because difference is too high. Okay, so it will again go like this. So if we plot the line, right, what will happen? You are getting exactly parabolic line, correct? What this parabolic line says? Basically, whenever you are going to have slope 0, you are going to have very maximum error. But as you approach with different slopes, your error is basically decreasing. You see here? And that's what we want. When exactly it is increasing? So it decreased till here. Exactly at this point. After that, if you again increasing the slope, your squared error is going to be high. Again it will start increasing. So exactly at what point your sum of squared error was minimum? This is the point. Okay, so this is what we are interested in to find out, and that's where your best fit line will come, where your global, this is also you can take as global minimum. Out of this whole parabolic equation, where is my global minimum? Okay, if you are able to find global minimum, that's where your this slope is going to represent as, let's say, 0.4, 0.6, 0.8, and 0.4. I can make this as a slope where global minima is present. Global minima is present, and that's what we are finding out based on that equation while during multiple iteration. Okay, so based on this, you found global minima, and you found the best fit line also, correct? But you see here what is happening when there are too much differences, right? So you are going to add the penalty. Okay, when slope is too high or too low, right, you are going to add penalty, and that's what you are going to regularize the data, okay, with the help of Lasso or Ridge regression. So we are going to add this slope square in case of ridge regression. Okay, so when you keep adding like this, right, so what will happen? Lambda equal to 0 when you had best fit line. Okay, if you add, let's say, lambda equal to 10, Okay, and your slope was, let's say, 0. So anyway, it is becoming ordinary least square, but lambda equal to 0 and your slope equal to 0.2. So 0.2 square, it will become 0.04. Okay, 0.04 into 10. Okay, you will get some value. Okay, so keep doing like that, and finally at the end you will see what is happening. Your slope is moving towards 0, not exactly 0. That's what is happening in the ridge regression. It will move towards 0, but not 0. Okay, so as you increase the lambda value, it is moving towards 0, because more the value, more shrinking will happen. Okay, because it is moving towards 0. If you keep plotting line like this, right? So let me just plot another line. So let's say you have another line which is your global minima like this. You are plotting another line with the help of different lambda, right? So you'll keep getting parabola equation like this, but there is it is going to touch close to 0. This point will be always close to 0, not exactly 0. Okay, that's how it is shrinking the curve. Okay, parabola curve. Okay, and it is optimizing the calculation to get the global minimum, and because of that you are able to avoid the overfitting with the help of ridge regression. Okay, so this is the mathematical intuition, and you just remember, as you increase the lambda, your slope will move towards 0. It is very much close to the 0. Okay, so due to this, it is going to add very less weightage to the those feature which is very much close to the 0. Okay, that's how it can avoid overfitting. Okay, so overfitting we already know from the previous video, right? You can get either you are training the data too much, or you have a lot of features lesser than the number of observation. That's where overfitting will come into picture. So you keep increasing the slope, and a lot of feature will move towards 0, but not exactly 0, and that's how it can avoid the overfitting. Okay, so that's about the ridge regression. Now in case of lasso, what happens? So very much similar data I'll take. Okay, so this is your best fit line where lambda equal to 0. Now if you keep adding lambda more, right? So let's say this is my parabolic equation. This is your slope, and this is your sum of squared error plus lambda, that is penalty, multiplied by absolute value of slope, not the square. This is the difference. Okay, absolute value of slope. So what happens basically when you take lambda equal to 0? So this is basically your best fit line, and this works as like same as 1 upon 2n and I equal to 1 to n y minus y hat to the square and plus lambda. The moment you set it 0, this has whole equation has become 0. Only this part is remaining. This is as good as your ordinarily least square or simple linear regression. That's what we got the best fit line. Now you again assume you have the data, let's say lambda equal to let's say some 10 value, and your slope is 0, right? So what will happen? Your square will be here. Okay, and similarly here, here. So this is the best fit line you are getting, correct? This is the best fit line, and assume that this is something somewhere near 0. Okay, because this is your global minima, right? Assume that it is moving like this. This is your global minima. Okay, now if you are increasing the lambda, let's say you got lambda equal to 20 and lambda equal to 30, and you are increasing degrees in slope also. What will happen in case of absolute value of slope? What is happening? This, whenever you are going to plot another parabolic for a different lambda or different slope, right? What is going to happen? It is exactly your absolute value will be exactly at 0. So from here you will start seeing the crank. Okay, and it will sync the graph, but you are exactly, there could be some feature where it is going to hit exactly 0, not close to 0. Okay, so these are various value of lambda. Okay, so let's say this is your lambda equal to 0, because this was the best fit line. This is lambda equal to 10, this is your lambda equal to 30 based on various value. Lambda equal to 40, and let's say you are giving lambda equal to some high value, very high value, right? So you see here, it is always going to hit the 0. Most of the feature where which is not at all going to contribute to your predicted data, right? It is going to set the 0. Okay, but in case of ridge, it was moving towards the 0. This is also shrinking, but it is almost at some feature has almost set to the 0. Okay, so whenever it's set 0, we can also reduce. We can assume that those features are not going to contribute to much for the prediction. I should mention like this: not going to contribute much for the prediction. Okay, basically it is not going to add much value whenever you are doing the prediction. Okay, so this technique, because of this, because it is going to set the 0, right, it is also this feature or this lasso regression can also be used for feature reduction. I'll talk about this later once I talk about the feature engineering, right? How you can reduce the number of feature reduction techniques. So we will run lasso algorithm, and once we get the coefficient right, there could be some feature which is exactly going to set as 0, and that feature we can remove it from the prediction. Okay, while running for the prediction. Okay, so that is the main difference between lasso and ridge. So remember that lasso will have absolute value in the penalty term, and the ridge will have square of that slope. Okay, in the penalty term, and in the lasso, a lot of feature will move exactly to the 0, which can be used for the number of feature reduction. But in case of ridge regression, it will shrink the uh, graph or parabolic curve by optimizing the value in such a way that it is not moving towards, it is not exactly 0, it is moving towards the 0. Okay, and that will avoid the overfitting of your curve or overfitting of best fit line. Okay, so these are the two differences, and this can be asked in an interview. So exactly you remember the formula, and this kind of graph will definitely help you. Okay, so let me go back and load the data. Before loading data, you just remember these kind of library what we are exporting, importing from the Python library. So one is linear regression. Anyway, we are not going to use it, so I'll just remove it. So we are going to run lasso and ridge, and data set will use load Boston function, by which we can use the Boston house price prediction data set. Okay, trend split I'm not going to use right away because I'm going to run whole data as a trend, because here goal is to see how lasso and ridge works. We are not exactly working on train and test split data. Okay, and polynomial feature, these also not required, and RT score to measure the goodness of the, how good is your best fit line, how good is your data. um, like higher the score means your best fit line has been good or your model is good. Okay, so let's go ahead and load it. So how to load? Let's load in the form of load Boston. Okay, you can directly get X and Y by making, there is one parameter called, or I'm going to load in a different way. Okay, data equal to load Boston. Okay, data if you load. So here we have data, so all the data and their target values and what is their description. Okay, so if you want to put like this, data dot, what shall I use? So let's say data dot data. Okay, so this is the array of data, and data dot, we have something called feature names. Okay, so let's talk about what feature it contains. So we have cream Z, and if you want to know what exactly those data description means, we have something called description, DESCR, data dot, and let's print them so that it can print in a proper format. Okay, so cream is nothing but per capita crime rate by town. So all the full forms are given, so you guys can just read it to understand better about the data set. But all we know is, like, we have how many features. Let's talk about this data, where it is. dot data dot shape. Yeah, so we have total 506 observation or the readings of the data and total 13 features. Okay, and what is the target value? We have data dot target. Okay, so the based on different 13 feature, whatever is the value of each feature and what is their price of the house. Okay, so that's what is mentioned. Now let's go ahead and create the lasso regression. Okay, so lasso is the function and I'm going to create ls as variable name. Okay, let's go ahead, and by default it will have some alpha. Okay, that alpha is nothing but the lambda value. Okay, so by default it is 1.0. You can put any value. So based on that, it is going to increase and decrease based on finding the global minimum. Okay, so once it is done, let's go ahead and do the fit. So ls dot fit, what data I'm going to fit? Data dot data. Okay, and data dot data is nothing but your x. So what you can do here, I just showed you all the description, right? I'm going to load the data again to make it more simplified version. Okay, why? This is just for your reference. Load data, and here there is one parameter called return xy. Just make it true. Excuse me. So whatever data you saw, right, you were filtering separately, like getting the data, description, target, and all those things. If you make this true, by default, it is going to add all the data here. That is independent variable and dependent variable y. That is what we are going to predict, right? So it will fetch them separately. If you want to see that, you can see this is your x and this is your y. Okay, now let's go ahead and here while fitting, we can give the x, that is for training data, and y is for your target training data. Fit it, and now let's do the prediction. So y pred equal to ls dot pred. Okay, and here is my predicted data. I'm going to use x, same data. So whatever we already have the y value, right? We are also predicting with by after the training. So we'll see how much difference is there. Okay, so what we'll do, I'm just going to hide this value to make notebook more clean. I'm just going to put plt dot scatter and x, not x, basically length of, sorry, range of length of y versus y. Okay, this is my original data and this is y pred. Let's use some color equal to let's say red, and here I'm going to set alpha 0.2 plt dot show. Let's make it a little bigger. Figure fig size 16 by 4. Okay, so whatever blue you see, right, that was the original data, and what we predicted is nothing but your red data. Okay, so I can add one label also, label equal to y true, and this is nothing but y pred, so that you guys can understand data. Okay, plt dot isn't. Okay, so y true is this, and while in it is like more or less very much same, right? So because we have used whole training data, we haven't split train and test, right? So whatever training we did, we are using same data for testing also. Okay, so that's what. So if you are going to plot best fit line, it can be plotted, but I just showed the scatter so that you can see how data is overlapping. Okay, but this is the prediction. Now let's see the score. How much you can score here. So this is your y actual data and y pred. Let's see the score now. See here, we are getting almost close to 68% score, which is not good, not bad. Okay, more than 50 is like, it is okay, not very good. Now let's see how we can increase it. So before increasing, I'll show a couple of features which has already been set as 0. Okay, so those features are not all adding any much value for the prediction. Okay, so how we can get this those feature? We have something called coefficient. Okay, you see here, 0, 1, 2. This is the first feature which has some value, second feature some value, very close to 0, but not exactly 0. But these features are completely set to 0. Means these features are not at all adding much value in the prediction, so we can remove them. Okay, so how to remove them? Let me do one thing. I can plot the graph also for getting which feature is having more meaningful and which feature is getting 0. Okay, so what we can do here, we have data load Boston df, not df, let's say data df equal to pd dot, I'm going to create data frame. Okay, then it will be easy for us to filter only those particular feature which is not at all having 0 values in the coefficient. Okay, so data equal to data dot data, then columns are nothing but data dot features name. Okay, what is my feature name here? I can get from here. There's a feature name. Yeah, this is the one I was looking. So I'll use this as a feature name. Okay, now what is my df? This is my data frame. This is having all the feature and complete observation. Okay, but here only there are some feature which is not at all contributing. Let's say chas. Okay, this is already 0, so which is not contributing much value. There could be other feature called zn. This is also having some value in some observation, but a lot of other values are 0, so they are not at all contributing much for the prediction. So that's what, for these features only we have got 0 value in the coefficient. Okay, so let's find out how we can filter the value based on this. So what I'll do here, df, where df dot so I'll just take ls dot coefficient df dot columns. I want to get only those names where this is not equal to 0. Okay, so this is the value I got. Now from this I can filter from complete data. This is my final data where all those features have been removed. Did we remove zn is having something, so this is contributing, but if you see indus is not there. Okay, and what else? chas is also not there. Okay, yeah, so now we got the value, and so these are the feature which you can later use it for. This is the new data set after removing the feature. So this is also known as like feature reduction we can do. Okay, so here if you want to see how much feature we are getting, what is the shape, see here. So from 13 we came back to 10. Okay, so you can reduce further if any collinearity is seen again between the features, it is going to set the 0. Okay, so that's how we reduce the feature and we will improve the accuracy of the model. Okay, so that's about lasso. Now let's go ahead and see the ridge regression. Ridge regression. Okay, by the way, I wanted to show the graph also, right? So here we have plt dot plot and df dot columns, df dot keys I'll take, and y is nothing but ls dot coefficient. Okay, and let's put the plt dot xticks rotation equal to 90, plt dot show. Okay, you see here, so these are the value which is very much close to 0. Zn cream is Zn is having some value, so it is not set exactly 0, but cream is 0, not 0. It is also having some negative value. If you see here, indus is exactly set as 0. You see here this graph, this point. Okay, after that nox is also set to 0. And what else? Probably tax. Okay, so only 2 or 3 features have been removed, right? Like b is also set to 0, right? So these are the feature which is not having any significance in the prediction. That's why it got removed. Okay, now let's see the regression. So I'll take the same data here. So let's take only this value. Okay, so what I'll do, I'll just make xy and load Boston, and here return equal to true. We'll quickly do the regression model. So this is ridge, so I'll just create another object ri ridge. Okay, here also if you see alpha is by default set to 0, you can put any value. Okay, now we are going to ri dot fit. We are going to fit the x and y. Okay, now we are going to do y pred, prediction of x. Y pred equal to ri dot predict x. Okay, now let's do this plotting. How does it look? Yeah, so here we have this prediction, and this time I'll go with blue color. Okay, maybe I'll give green. Okay, so this is also having very much prediction predicted value, but as I mentioned, right, in the lasso we have penalty as a square of the slope, right? So due to that, a lot of feature, it is not going to set 0, but it is going to move very much closer to the 0. Okay, and it will optimize very properly so that it will maintain the parabola curve, and it will find the best fit line for that. So let's see how much we are scoring. So y dot fit. Okay, you see here, the score is almost more than close to 10-15%. Okay, earlier we got almost 60, and here we have close to 73% accuracy, so which is quite better than lasso. So that's how you evaluate the model, okay, using R2 score. So out of these two, of course, ridge regression is definitely going to provide a better model. You can still do further optimization, okay, by various techniques we'll see in the feature engineering also. Okay, but as far as lasso and ridge regression concerned, lasso, if you are going to use lasso only when, let's say, you want to do a lot of feature reduction where n number of features are there. Okay, and ridge you can definitely use for improving the model or improving the overfitting or to avoid overfitting. Okay, so that's all about this, guys. And yeah, what is ridge and what is Lasso regression? These kind of interview questions we ask. What is their mathematical intuition and where exactly it is? So when it comes to where, so whenever you are going to do feature reduction, go with the Lasso. Whenever you want to avoid overfitting, Lasso is also fine, but ridge is much better than Lasso. Okay, so that's all for today, and see you with next algorithm in the next video. Okay, thank you so much. Bye.